One of our main goals will be to find a way to calculate real valued integrals, not by doing some complicated calculus, but rather by having a shortcut which involves straightforward algebra. So that sounds very promising. And a key concept in that scheme is the concept of the residue of a complex function in a certain point z0. So how do we define the residue in a point z0? Well, the first thing we need to do is we need to develop that function f of z in a Laurent series around the point that you're interested in, so z0. So we're going to write that f of z is the sum of m going from minus infinity to plus infinity, a sub m, z minus z0 to the power of m. Okay, that we know. But the question is now, what is the residue at a point z0 of our function f of z? Well, that's nothing more, nothing less than the coefficient of 1 over z minus z0 in this Laurent series. So how do we calculate that coefficient? So if you go back to a calculation we did earlier when we were looking at the Laurent series, we ended up with this complicated expression that gave us an explicit formula for each of the different coefficients in the Laurent series. So what we're interested in is the coefficient minus 1, so the power of 1 over z in this case. So remember, this was developed around the origin, but you can just as well replace z with z minus z0. If we want minus 1 here, we see that we need to have n equal to 1 in order to find the coefficient. And then that will give us that a minus 1 is 1 over 2 pi j. And then we have the integral of f of z prime dz prime. And then for the denominator over here, you see if we have n equal to minus 1, that just gives us 1 in the denominator. So here we can already start seeing why residues are important, because there's a clear connection between the residue, this a minus 1 coefficient in the Laurent series, and a contour integral of the function itself. And this is a key observation that will come back later, of course. Now, just to wrap things up, some small examples of calculating residues. So I suggest you pause the video and you calculate the residue in the origin of 3 different functions, namely the function 1 over z, the function 1 over z prime, and then the function exponential 1 over z. So pause the video and quickly try to calculate these residues. So obviously we don't really need to calculate these contour integrals for these specific cases here, because for example, if we look at the first function 1 over z, well, in this case the function itself is already its Laurent series, and it's a bit of a special case where the Laurent series only consists of a single term, and moreover it's the term that we're interested in, the term 1 over z. So in this case we can say that the residue at the origin is just 1, because we have 1 times 1 over z. Likewise, for the second function, 1 over z squared, again, a Laurent series with a single term. And in this case, we see that the coefficient of 1 over z, well, there is no coefficient of 1 over z. So in that case, the residue in the origin is equal to 0. So by the way, it does not, you can't really say that if you have a residue which is equal to 0, that you do not have a singularity. I mean, this example clearly shows you have a double pole here and the residue is 0. Of course, the other way around, if you do have an analytical function, you have no negative powers of z anywhere, and therefore also the residue is equal to 0. But don't turn this around. It's not because the residue is 0 that you don't have a singularity. Finally, exponential 1 over z. Again, here we already know what the Laurent series looks like. We have our famous series expansion, the sum of m going from 0 to infinity, the argument of the exponential, that's 1 over z in our case, to the power of m, divided by m factorial. So what we're after here is the coefficient for m equal to 1, and in this case 1 factorial is 1, so the residue here is also equal to 1.